Hello, welcome back. In this segment, I want to prove the probability that the algorithm will successfully factor n given n, e, and d. The goal is to find the prime factors p and q. The way this algorithm works is that we randomly select a group element x and compute this sequence x power u, x power 2u, and so on. And we are looking for a particular pattern. If one element is not equal to plus or minus 1 and the next element is 1, then we are done. We just compute GCD of y plus or minus 1 with n. If I call this particular element as y, the next element is y square, right? And if y square is equal to 1, then we have explained how to find the prime factors of n. The question now is, what is the probability such an x exists, right? Well, it's easy now. We have proved in the previous segment that there is a set called BAD, and BAD is a subgroup, in fact, of the group Z star n. So we have also proved that the size of let's say this is Z star n, right? And we define a set called BAD. So we should avoid selecting elements from the BAD set, right? If you're randomly selecting an element from this group, we should not go to this BAD group, because BAD group contains elements that are not useful for us to factor in. And we proved earlier that BAD cannot be more than half of the group elements. Okay, so BAD can be at most half, which means in one iteration, what is the probability? Let's say I randomly pick an element x. Okay, there are two possibilities, right? X is outside BAD or inside BAD. But as I said, BAD is bounded by the half of the size of the group Z star n. We proved it earlier in the previous segment, which means we have at most half chance to land in the BAD group, right? Okay, if we land inside BAD, we are out of luck. Okay, we need to try another x. As soon as we find an x outside BAD, we are done. We can factor n, which means, what if we do this process of selecting x t times? Every time we try, let's say we have a bad day. Okay, every time we try, we end up with BAD. Okay, what is happening in that case? We select an x, it end up in BAD. Okay, what is the probability that can happen? At most half of the group elements, right? That means at most 1 by 2. Okay, let's even take 1 by 2 conservative estimation, first attempt. And the next attempt, another 1 by 2. And they're all independent. Okay, so I can multiply probabilities, which means I do this t times. Okay, what will happen now? Which is nothing but 1 by 2 power t. Okay, if I make my t to be, say, 40, then how many trials I will be doing? Let's say in all my 40 attempts, okay, if I end up in this BAD, which is, what is the probability that can happen, is 1 over 2 power 40, which is pretty close to 0. All right, you can also reason about it this way. If you set t to be 40, okay, you're going to try 40 attempts. What is the probability in all the 40 attempts you end up inside the BAD? Okay, you're always selecting elements from BAD. That's 1 over 2 power 40 is the probability that happens. That's negligible, right? Almost close to 0. Okay, so that means, in other words, if your goal is to factor n from E and D, the private and this is public exponent, this is the private exponent. And if you set the number of trials to be 40, then you have a probability of winning or factoring n 1 minus 1 over 2 power 40. Okay, at least this is the probability that you are able to successfully factor your n, probability of factoring of n, getting the factors p and q. Okay, given n, finding the factors p and q. Probability of that happens by randomly selecting a group element is 1 minus 1 over 2 power 40, which means approximately close to 1, which means you will very likely succeed in factoring n. Okay, so we have established the formal bounds now that this algorithm will, with a very, very high probability, factor n given E and D as inputs. Okay, now let me show you the algorithm. Okay, we have been talking about it. We ran some experiments, but we can now see the algorithm. This is the source code of my factoring algorithm. It's going to factor from n, E and D trials. Okay, on the source code, I often prefer to use small n because that's usually the way people write variable names, the same as the capital N on the whiteboard. Okay, we are running t times. That's the outer for loop, at most t times. What do? We select a random group element. X is the random group element from Z star n, and we compute x power u, the first element in the sequence. And then remember, we have to compute this sequence of numbers. X power u, where is this happening? This is basically what is happening here. X power u, x power 2u is square of the previous term, and then x power 2 square u. All of this is computed until we find a pair such that one element is a square of the previous element. Okay, that's basically what we are trying here. This is going to be 1 always, because this is I approved on the whiteboard this will be 1, but anywhere here, suppose let's assume this is not equal to 1 and not equal to -1, and let's assume the next element is 1, then we are done. That's what we proved on the whiteboard, and that's exactly what's happening here. We take x power u, and in the loop we keep squaring the elements, and we check whether we get a 1. Okay, this is the next element is 1, and that means we check whether the previous element is not equal to 1 and not equal to -1, right? This is what we are saying here. Then we compute GCD of y minus 1 comma n. Okay, that's exactly what we talked about on the whiteboard. I'm introducing the variable z to store the y square mod n. So this is the piece of code that factors n given e and d, and it tries t times. Okay, when will it fail? It will fail, of course it will fail, but when? It will fail in all the t attempts. It was not able to find a pair of numbers such that one number is a square of the other number, and that number is equal to 1, and the previous number is not equal to 1 or not equal to 1 or -1. So we don't need the previous, we should not have the previous number to have the value 1 or -1, because that's not useful for our algorithm. That's the reason why we are doing this here. Previous element should not be equal to 1 and should not be equal to -1. In all the t attempts, if we violate this property, then the algorithm will return none, which happens with a very negligible probability, 1 over 2 power t. I talked about it on the whiteboard. Okay, that's basically the idea of how to factor n given e and d. All right, thank you very much.